All right. Okay. So my name is Rafael Quirino. This is a sample video of my lecture style. And so I'll start this video, talking about substitution reactions in general. My first slide will portray, a few examples of substitution reactions at that stage. I'll have not talked about SN1 and SN2 reactions just yet. So I don't differentiate between SN1 and SN2 reactions from the get-go, right? I just present substitution reactions as a whole, and then here I show the three reactions. I really want to point out what happens in those reactions overall, more so than the mechanism at that stage, right? So I point out that we need three pieces for those reactions. We always need a nucleophile. We need a substrate, and that substrate has to have a leaving group that's a part of the molecule that breaks apart. So if we look at those three examples, here we have three different alkyl halides, and then we have those nucleophile species. We're going to notice similarities between the nucleophiles we see in future slides. They are usually small molecules. They usually have a negative charge. And lots of lone pairs. This is going to configure a good nucleophile. We'll see details about that in a little bit. And then all of those molecules, in this case they're all alkyl halides, they have a halide, which is a good leaving group. So in the next slide we're going to talk about leaving groups and see what makes a piece of the molecule to be considered a good leaving group. Right? But if we look at what happens overall here, we have a nucleophile, comes along and it replaces a part of that molecule, right? And so in your products you get the same substrate, but then that little piece that we call the leaving group breaks apart here and stays by itself, and then the nucleophile comes along and attaches to the substrate. So overall what happens is the nucleophile comes along, it knocks off that chlorine in that first reaction, and then you get this as your major product, and then this that was originally attached to the substrate is what we call the leaving group. It breaks apart from the substrate. If we look at different molecules and what's going on overall, it's the same idea. It's always the nucleophile coming along, knocking off something on that molecule, a group, right, a piece of that molecule. That piece that breaks apart is our leaving group, and then the nucleophile replaces that leaving group in that molecule. So it substitutes the leaving group, and that's why those reactions are called substitution reactions. Okay? So what we're going to do in the next few slides is we're going to look at those three features. We're going to look at nucleophiles, we're going to look at leaving groups, and we're going to look at substrates. And then we're going to start talking about SN2 and SN1 reactions. Okay, so as we look at leaving groups, right, one thing that's going to determine how good a leaving group is the stability of that piece that breaks apart after it breaks apart from the substrate, right? So if we have a molecule that has water as a leaving group, and then that water breaks apart from the substrate and sits by itself as water, that molecule of water is very unreactive. It's very stable. So water is a very good leaving group, right? If we start comparing water with other molecules, in that case ammonia, for example, we can look at the basicity of those molecules and relate that to stability, right? So if we compare water and ammonia, ammonia is more basic than water. So ammonia is more reactive than water according to basicity, right? Therefore, water is more stable. Water is a better leaving group than ammonia, right? If we look down the same column in the periodic table, so if we take the halogens, for example, right, and we look at halides in that column, so comparing fluoride, chloride, bromide, and iodide, and start thinking about stability as well and basicity, we'll see the same trend. We'll see that fluoride is more basic than iodide, right? And then because it's more basic, it's less reactive. Because it's more basic, it's more reactive. Because it's more reactive, it's less stable. And if it's less stable, it's a worse nucleophile. So as we compare this, we get better nucleophiles as we go down the halogen column in the periodic table. We can also think about this in terms of the size of those anions, right? So iodine is a big atom. So iodide is an anion that has a decent size in comparison to fluoride. Fluoride is much smaller. So it's the same negative charge on iodide spread through a much bigger area in comparison to fluoride, right? That smaller size of the atom with the same negative charge will make that negative charge be more localized, and that will make it less stable. On iodide, that same negative charge is spread throughout the atom. It's a bigger atom, so it's a more delocalized charge of sorts, and that'll make it more stable. I typically tell my students that there's more space on iodine to accommodate that negative charge, so that negative charge, it feels not as strong as a negative charge on fluoride. So that makes iodide less reactive than fluoride, and therefore a better leaving group than fluoride. Okay. So at that point, I'll have a clicker question on my lectures. That's the way I like to give my lectures. I'll have PowerPoint slides, and then every now and then I'll have a clicker question that comes out, and then I ask the students to use clickers to answer that question. And then with the clickers, what I really like about the clickers is that it gives me a feedback. I can look at the answers the students are answering, and I can see if the majority of the class is getting the question right or wrong. So if the majority is getting it wrong, then that means that I need to go back and go over that material in a different way, using different examples or more thoroughly. But if everybody gets this question right, for example, then I can move on. It tells me whether or not students are really getting the material. I typically, have the question up. I read the question with them and explain a little bit. If it's not very clear, I'll explain. I'll point out, kind of like on this one, for example, I would say it's the same nucleophile. The substrates look pretty much the same. The only thing that's changing here is the leaving group, and so if we determine which one of those is the best leaving group, then we can know which one of these reactions is the fastest one. So I let them answer, I go through the answer with them, see if I need to go back or not on lecture, and then I move on. Alright, so we talked about leaving groups, right? Now we'll I start talking about nucleophile. And so the first thing I say about nucleophile is that there is two things that are very, very, very important on nucleophiles, right? The first thing is the size or bulkiness of the nucleophile, and then the second thing is, the presence of a charge or a negative charge or a lone pair that will make this molecule a nucleophile. That will make it a molecule that likes to go after nuclei, that likes to go after positive charges, right? So the size is easier to explain because I can just point out to molecules and compare, for example, ethoxide and butoxide and say, well, you can very clearly see on those molecules that this one is more cluttered. There's a lot more groups. Here is your oxygen, right? So if you compare a molecule like this with a molecule like that, which is ethoxide, this oxygen with a negative charge has a lot less steric hindrance around the oxygen. So this one can travel around more easily to react with other substrates, with other molecules. Whereas this one is going to have much more trouble going around and traveling around just because it's like a bigger molecule, right? So I'll point out this issue about the size or bulkiness of the molecule. And I like to summarize things and use terms that the students may remember more easily, right? So what I typically say is that in order for you to call something a nucleophile, it needs to be a small molecule or maybe a linear molecule, right? And then it needs to have typically a negative charge or lone pairs that can be used, right? So as far as size, it has to be small or linear, pretty much, right? I know it's not that clear cut, but as they're learning this will help them, grasp that concept a lot better. Then I talk about charges. Yes, those nucleophiles need to have negative charges and or lone pairs, and that's because they're called nucleophile philes. That's because they like positive charges. They like nuclei of atoms. The nuclei is positive, so nucleophiles like positive charges, right? So they typically have a negative charge or lone pairs to do that. Okay, and then I'll talk about solvents, and so I'll mention why, what kind of solvents we need. Polar solvents are good, and then non-polar solvents are not good for those reactions because of the charges that we have involved in those reactions, and so on and so forth. And then I go over product, aproduct solvents, explain them, difference, and say that this is going to have an impact on SN1 and SN2 reactions. I'm rushing a little bit here because I do want to get to, so I'll have another clicker question mentioning about polar and non-polar. I'll make the point that polar is the preferred solvent because non-polar will not even solubilize those things and things like that. But I'm rushing a little bit because I do really want to get to the substitution reactions mechanism, the SN2. I'm not going to go into the details, but I just want to mention that, so I cover those basic points, and then I get to SN2 reactions, right? That's the first mechanism that I cover. It's a concerted mechanism, and then what I'll do here is I'll have one example on the screen for the students to look at, and I'll point out, how the reaction happens. I'll point out that this is the nucleophile. The nucleophile attacks the substrate at the same time as the leaving group breaks apart from the substrate, right? So it's all in one step. It's two things happening in one step, right? The two things makes for the number 2 on the SN2 designation, right? It's a bimolecular reaction. You need two things, two molecules coming together at the same time, and then as for substitution and for nucleophilic, right? But then I just point that out, and then from that point on, I'll go to the board and I'll start drawing, other examples of similar reactions, of SN2 reactions, and so I'll give that to them. And from this point on, I'll start talking about the specifics of SN2 reaction, inversion of stereochemistry. I'll show the stereochemistry. I'll show other examples besides the ones that are on the screen, and so on and so forth. Right? So I'm going to stop my video right here. It gives you a little bit of an idea of how I teach. I would like, preferably, to teach that in a classroom environment where I have a board to switch from, slides and board. But then hopefully that will give you a good idea of what my lecture style is. All right? Thank you very much.